All right, hello, and hope you guys are doing well. I wanted to show you just kind of like a little fun thing that you can do with PCA. I don't know how fun this is, but um, I thought it was kind of a neat, maybe a neat application showing kind of how dimension reduction will reduce the, basically reduce the amount of data that you have to kind of keep, right? And it's kind of the idea of like, we're trying to preserve the maximum amount of variation, with kind of the fewest dimensions as possible. And so to kind of demonstrate this, I have this image of Audrey Hepburn from the movie Breakfast at Tiffany's, okay? And this image is 634 pixels wide by 791 pixels. Okay, and this is kind of a, I don't know, perhaps an iconic picture from, this is a movie from the 1960s. It's, I don't know, this kind of romance comedy thing. And but anyway, I just wanted to show you that we can try to kind of compress this image down to a lower number of dimensions. Okay, now this is not how image compression is done these days. So most of the time when you think of an compressed image, it's done via JPEG, and JPEGs use like wavelets and things like that. This is not how we compress images, although theoretically it could be used, okay? But it's kind of computationally expensive, probably not the most practical way. All right, so just to kind of demonstrate how this is going to work, I'm going to load up this package called Imager, which allows me to kind of display images here, okay? And then we'll load this up, and then we're going to load in the image. Oops. Okay, so the image has been loaded, and if you take a look at the dimensions of the image, it says 634 by 791. There is one frame. It technically supports like GIFs and animations in case you have like multiple images in like a video. And then there's also three colors, red, green, and blue. But in a black and white image, a grayscale image, all three channels, all the red, green, and blue, all have the exact same values. And so, so we can just kind of throw away those extra things. So what I'm going to do is I'm going to take this this array and then just reduce it down to a 634 by 791 value matrix. Okay, and you can plot this. Okay, and here it is in R. We are plotting the contents of the image here. Okay, and this is it's a large matrix, 634 by 790. 634 times 791. It's got 501,000 values in this matrix. So it's a big matrix. Okay, and basically we can think of this as a matrix with kind of 634 columns. Okay, so this is a big matrix, right? So we can think of this image as a matrix, okay, with 500,000 values, and every value represents a pixel. Okay, every value is some value, either between 0 and 255. I mean, let me just kind of take, maybe it's between 0 and 1. Let's just kind of look at the first. Okay. So we've got values between 0 and 1. So in this top corner here, we have values close to 0 because it's dark. If I kind of go into this region, looks like maybe 250 by 200. 250 to say 260, 200 to 210. Okay, we have values of like say 0.97, right? Because these values are closer to 1. Okay, so values that are have the value 1, okay, pixels with the value 1 will be white, pixels with the value 0 will be black. And so, you know, this top corner up here is going to be low values. This area out here is going to be higher values. Okay, and so what we're going to do is we're going to try to do some image compression, and here we can treat this as a data set of 634 columns, and we can treat each column as its own variable, right? And we can say, you know, are any of these columns kind of correlated in some way? And I would say, yeah, you know, when you look at a column, the values in one column are going to be very similar to the values in the column right next to it, right? Like if you think of just like one column of pixels here, and you take another column of pixels right next to it, basically those columns are going to be quite similar overall. So there's going to be a high correlation between each of these columns, at least each column with its kind of its adjacent column. We expect there to be some high correlation. And so, you know, can we kind of reduce this somehow? All right. So, so that's what we're going to do. So in order to do this, what we're going to do is we're going to kind of go through the process of finding principal components. And so to find principal components, what we're going to do is we are going to center our matrix. All right. So this is a matrix 634 by 791. We're going to center each column. Each column is going to, all 634 columns, we're going to subtract the mean from each column, and that's going to say the mean of each column is going to be 0, right? So I'm going to calculate the means, okay? And so now I have 634 values for the means, okay? Odd is short for Audrey Hepburn, okay? And what we're going to do is we're going to subtract the means from every column in our matrix, okay? And so my centered matrix is going to be this. Odd centered is going to be my centered matrix. So it's going to have, it's also 634 by 791, but now every column has a mean of 0, okay? And we can kind of, we can check, and I'm going to just check, is are the means of all of the columns equal to 0? And that comes back, and it's true, right? And I just kind of want to plot what the centered image looks like. Okay, and this is what it looks like, right? So what I've done is I've subtracted the mean of each column. Okay, I've subtracted the mean of each column, and so what we end up getting is this very kind of image with all of these streaks, and it seems kind of a little bit washed out now. Okay, and basically what we're doing is that, you know, if you take the average, okay, if you take the average of this whole column, the average of the whole column is now going to be 0. Okay, and so what we see here is that if you think of the column of pixels in this line here, there's a whole bunch of bright white pixels here, and so the average of this column is going to be a lot higher. And so when we subtract that, you know, these pixels end up getting quite a bit darker. Okay, whereas if you look at this column right here, where it's kind of like a lot whiter here, a lot lighter here, what's going on there is if you look at that column of pixels, if you look at just kind of one thin strip going straight up and down, she's wearing this black glove, okay, this dark colored glove that shows up black in the image, okay, and so the column, that column has a kind of a lower mean, right? So its column, you know, you're subtracting off a very low value, or you're possibly even adding values back into it, so it's gonna end up somewhere different, right? So in this column where there's kind of a lot of white values in this thin strip, when you subtract off the mean, it ends up kind of darkening these values up here. And in this column of pixels, this thin vertical strip of pixels, there's a lot of black pixels. And so, to kind of average it out so that the whole column average ends up being 0, it ends up having the effect of kind of lightening these things, right? So anyway, we get this streaked image, but this is all to say is this is what the image looks like if we just center it so that every column has the same mean. Okay, so if you take the average pixel value, the brightness and darkness of every column here, the average is going to be the same across the image now. Is that okay? As far as what centering the image and what effect it has on the, or centering the columns and what effect it has on the image. Okay. All right. And so now what we're going to do is we're going to do principal components analysis. And the way we're going to do this is we're going to find the covariance matrix of our centered data. So I'm going to say ask for the covariance matrix. Okay. And so the covariance matrix is going to be huge, right? We got 634 columns. So your covariance matrix is going to be 634 by 634. Okay. You now have this very big, big matrix, 401, 956, and that's found by doing 634 by 634. It's this big matrix. And what we're going to do is we're going to find the eigenvectors of this covariance matrix, right? So I've got this big square matrix, 634 by 634, because original data had 634 columns in it. We're treating each column as kind of a variable. And we say, what's the covariance between each of these things, right? And so some of these columns, which this column of pixels, which is kind of adjacent to other columns of pixels, those are going to have high correlation. And so you're going to have some of these values in here are going to have high covariance, right? So if I take a look at covariance, and let's just take a look at, say, the first 3 columns. I guess there's not, the correlation matrix. I didn't calculate the correlation matrix, but if I did, let me do, if I did the correlation matrix of Audrey centered, you're gonna see, some very high correlation between kind of adjacent columns, right? Which kind of makes sense, right? It's kind of like, do the pixel values in this column, are they similar to the pixel values in the adjacent column? And it makes sense, right? And as you go farther and farther apart between pixel values, we expect there to be kind of less correlation or less covariance. All right, but anyway, we have the covariance matrix here, and we're going to ask for the eigenvalues of the covariance matrix. Okay, so I'm going to just say eigen of the covariance matrix, and we'll take a look. When you look at the structure of the results of calling eigen on a covariance matrix, the results are going to be, you're going to get a list. You get one, which is the eigenvalues, and then the second will be the eigenvectors, okay? And you're going to have the eigenvectors itself will be this large square matrix, 634 by 634, and each column is going to represent kind of the linear weights that we would use to create a principal component. Okay. Is that okay so far, what we've done so far? All we've done is we've centered our data and we found the eigenvalues and eigenvectors. And we have 634 eigenvectors, each of them being of length 634. Okay, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter B. B as in bear. B as in bear is your first view quiz answer. Okay, so what I'm going to do is I'm going to just say, let's keep the first 50 principal components. Okay, so I'm going to take my eigenvectors result, and I'm going to just truncate it, or I'm going to just take the first 50 columns, and I'm going to say these are going to be kind of my first 50 principal components directions here. Okay, and so if I ask for the dimensions of the first 50 principal components, it's I've got 50 vectors. Each vector has 634 weights for how we're going to combine the different 634 columns in our data set. And so what I can do is I can take this entire matrix, which is 634 by 791, or 791 by 634, and I can multiply it by my principal components weights matrix, which is 634 by 50. And so if I do that, what we're going to do is we're going to say, okay, take your 634 things, and here are 50 kind of ways to combine the different things. Okay? And so when I do that, the resulting data is a lot smaller. The resulting data is 791 by 50. So we've reduced the projected data doesn't show up as large matrix. It's now 791 by 50. Okay, so 791 by 50 has 39,550 values versus 501,000 values, right? So we've reduced the amount of numbers that we have to store. Okay. Now, if you were to try to plot the data just compressed, right? If you just try to do this, and if you were to try to plot this, it would be complete nonsense. Okay, there would be nothing. There's nothing intelligible to gain from plotting this. Okay, this is the image, 791 pixels high, 50 pixels wide, but it's not really 50 pixels, or it's 50 values wide, and it's impossible to get any kind of understanding out of this. Okay, because this is the result of this is some strange projection. We're getting just this weird shadow, and looking at this, we can't make any kind of sense out of it. The data exists in 634 dimensions, and we've reduced it down to 50 dimensions. Okay, but what we can do is we can transport this. We can transport this smaller matrix, which only has 39,000, less than 40,000 values in it. And using that, we can try to recreate the original data. Okay, so we can take this projected data and we can try to recreate the original data by undoing the projection, right? So it's kind of like, you know, here's my hand, and I've projected it down to a shadow, and it'd be like taking that shadow, putting it on a piece of paper or a cardboard, and cutting it out, and you say, well, now look at this. Now you have this three-dimensional thing that looks kind of like your hand. And that's basically what we're going to do this. We're going to take this reduced data, 50 dimensions, and we're going to project it back up to 634 dimensions. And we're going to see, okay, does this reconstructed image look anything like the original image? Okay, so I'm going to do Audrey reconstructed here, because we're going to take our reduced projected data, which again only has 40,000 values, less than 40,000 values, rather than the original 500,000 values. Okay, when I reconstruct it, now we're back to 791 by 634 values. So when we reconstruct it, it's again full size, and we can add the column means back to see what the original kind of what the image looks like. Okay, and so here I've reconstructed it, and I'm going to plot it now. And this is the image. Okay, this is the image that we have reconstructed from after reducing it down to 50 principal components, or 50 columns of data. Okay, compare that to the original image. So here's the original image, and this is, I don't know how well you guys can see it. So the reconstructed image from kind of our reduced data set looks very much like the original image, but it's a lot kind of blurrier. It's a lot, it looks kind of pixelated and like like the results of image compression, right? And there's a lot less contrast in the data as well. Okay, is it noticeable for you guys viewing through Zoom, the thing? Okay, so if you think about it, it actually kind of makes sense what's going on. What we're trying to do is we're trying to preserve as much variation in the image that we can in this kind of reduced data set. The only way we could actually preserve the full amount of variation is if we preserve all 634 columns. Okay, if we preserved all 634 columns, that would contain the full data of the original data set. Okay, by reducing it down to kind of 50 columns or 50 principal components, I'm losing a lot of variation. And when it comes to an image, what is variation in an image? Variation in an image will be its contrast. The contrast is how different is the brightest part of the image versus the darkest part of the image, right? So high variation in your data set means you have big values that are very different from your low values. Low variation means your high values and your low values are not that far apart, right? So low variation means your values are similar. High variation means the values are very different. And when you talk about an image, how bright are the brights and how dark are the darks is going to be, you know, how much contrast do you have in your picture? Okay, so this would be there's high contrast, and here there's a lot less contrast, right? Where the difference between the brightest part of the image, which is probably this, I think it's an open window or door, and you know her dress, which is black. You know, the difference between that and that, you know, there's a significant difference, but you know, certainly not as distinct as in this image. Okay, and that's kind of what's happening when you reduce the number of principal components. You know, when you reduce your dimensionality, you're going to lose some of the variation, but perhaps the amount of variation you lose is not that big of a deal. And so, you know, this is going to come down to how much preference you have in your image compression and whether this image is acceptable or not acceptable to you, right? And so, you know, this idea of contrast, the contrast ratio is kind of an important selling point when you're like trying to buy a TV. Sometimes when you're trying to buy a TV or a monitor, they'll say, you know, that you have this 1,000,000 to 1 contrast ratio. And what they're trying to say is that you know, if there's a bright part of an image versus a dark part of the image, you know, there's a very large difference versus, you know, maybe a cheaper TV won't have as much of a contrast ratio, less variation between the brights and the darks. Okay. All right. And so here I ran this loop that that goes through, and it does basically the same kind of thing that we did, where we reduced it. Here I chose 50 principal components arbitrarily, but I just wanted to see, you know, what will our results look like if we picked only, say, 1 principal component or 2 principal components or 3 principal components. Okay. And in each of those things, what we do is I keep only a k number of the vectors. I project the data down to that. And then I reconstruct the data from my kind of crushed image set, and then I save it. Okay, so I've already ran this, and so I kind of want to show you, and I hope this works. I don't know why it's so small here, though. I don't know why. I don't know what's going on. I'll zoom in here. Okay. All right. Well, here it is with just 1 principal component. Okay. So when you keep, let's just put the original image for reference here. So if you take all 634 columns and you reduce it down to 1 column, and then you say from that reconstruct the image. Okay. So there's some kind of, you know, it's compressing the 634 columns down into one thing. And this says this is the most amount of variation that I can kind of capture. And this is not a good representation of the image. Okay. all we managed to do is kind of preserve, there's a bright region of white here, and there's also kind of a bright region of white there, but that's about it. Okay. If we look at the, how do I do the next image? What's going on? Okay. If we look at the, here it is, preserving two principal components. Two principal components, we get a tiny bit more structure. Okay, my computer's bothering me, but we get a little bit more structure. And again, it seems the principal components analysis seems to be drawn to this kind of this bright window or door that's shining kind of a high amount of light through. And so it kind of preserves that structure. We get kind of the contrasting darkness here. We get a little bit of dark over here, but that's about it. And then maybe some bright white areas here. So this is it with keeping just two principal components. So again, the idea is we've reduced all 634 columns down to two images, or two columns. Okay. With 3, we get it's still incomprehensible. And let's go ahead and try it with 4. Okay, and so it's just, a little bit more, 3 versus 4, maybe a tiny bit more structure with the 4. Here we're going to look at 4 versus 5. And again, how much of a difference is there between 4 and 5? It's kind of hard to tell. Let's go ahead and look at when you keep 6 principal components. Okay. And suddenly, with 6 principal components, something starts to emerge here that looks like it could be a face, right? You start to see something dark here and dark here, which would be her eyes. Okay. And you have something, if you have this for reference, you can kind of see, okay, I'm starting to see where this is going. But again, it's not much to go off of. With 7, you get a little bit more structure, and and this is going to be just kind of a as we go further and further, as we add more and more principal components, as we keep more and more of these dimensions, reducing from 634 dimensions down to 8 dimensions, we're losing a ton of information. Okay. I mean, I don't know if I want to go through every single one of these, but here it is with 9 and 10. And now I'm starting to skip. Here it is with 12, 14, 16, 18. So at around 18, you might be able to recognize that this is a person with arms and there's something. Okay. So at around 18 principal components, we've got enough structure here. Let me kind of just go ahead and skip. Sorry, that's 16. Let's go ahead to there's 25. Here is right. So how much of a difference is there between 18 and 30? 30 looks better. 35 principal components, 30 versus 35. So as you keep more and more of these, the image quality improves. Again, each of these things requires us to store more data, right? This is kind of what we showed with 50. Here it is with 70 principal components. So at 70 principal components, it's starting to look pretty good. At 90 principal components, there's not a ton of improvement between 70 and 90. I don't know, some improvement, okay? And you can even see at a certain number, it starts recreating the watermark in the image, okay? Because it has no idea what's actually an important feature keep. It's just trying to recreate as much variation that showed up in the original image. And then, if you go to say like 120 principal components and 150 principal components, at this point, the image doesn't get that much sharper, but you get a little bit more contrast, okay? So again, the darker parts of the image seem darker and the lighter parts of the image seem lighter. So I'm just gonna leave up 120 and I'll just kind of jump up to say 210, okay? And so with 210 principal components, we can see, better contrast in this image versus this one. And then, if I go up to say 400 principal components, at 400 principal components. So, at 210 and 400, I don't know if we're getting that much of an improvement, but this thing, I have to store basically twice as much of the data as I do over here, okay? To kind of get this much more variation in terms of the contrast between the bright and the dark, I have to store almost twice as many columns of the data, going from, I've reduced it from 634 dimensions down to 210 dimensions, and I can recreate this image. Over here, I'm going from 634 down to 400 dimensions, and I can recreate this image. All right. Is there a huge difference between these two? Not really. Okay. You do get a slightly improved contrast, but I don't know if it's that dramatic. Okay. And again, if you compare 120 versus 400 versus 200, which of these images look the best? Probably people would say the one with 400 looks the best, but then how much are you gaining, right? And again, all of this comes down to how many when you project your data down to the lower dimensionality, you really are reducing the amount of data that you have to store. And so this makes sense if you had to if you had to transfer an image, say from a internet server to someone's computer at home, and your internet connection is very slow, right? So I don't know if any of you ever used dial-up internet, okay? But in the days of dial-up internet, the internet was really, really, really slow, and so we relied on image compression in order to be able to look to see images that didn't take forever to load, and this could theoretically be a useful way to transport images, right? You reduce your image from say 791 by 634 pixels to a matrix 791 by 50, and then you also have to kind of provide it with the principal components instructions, and then the computer can recreate the some compressed version of the image. Okay, so we can recreate this compressed version of the image because we've transported a lot less information. Now, at a practical level, this is not how. There's no real commonly used image format that uses principal components analysis or this kind of dimension reduction to transport images. But theoretically, it could work. I think the reason why it's not used is because it's computationally expensive as far as computing all of these things and asking the computer to recreate these images, kind of was an expensive computational task, especially, I mean, today it's very quick, but back in the day, these kind of matrix operations and the eigenvectors were a bit more computationally expensive, and so this is not how we transport images, but in theory, something like this could work. Okay, I guess that's a little bit of a shorter lecture, but I guess that's all I had planned for today, was just kind of doing this fun little demonstration, and I can share my code, and I'll put that up on CCLE along with kind of the original image, and you can kind of try you know, playing around with the ideas of compression and reducing the number of dimensions that appear. I don't know. Did anyone have any questions or any comments on this? So yeah, I don't know. I thought it was kind of neat, just kind of the idea of taking treating the image as if were a high dimensional data set and reducing it to something less. I think I've only given you one view quiz answer so far, right? So let me go ahead and I'll go ahead and give you your last two view quiz answers. Last two view quiz answers today are D as in dog and C as in cat. D as in dog and C as in cat. Okay, we'll just call it a little bit early. Have a good evening. We'll see you guys on Friday, and that'll be it. So take it easy. We'll see you guys then.